This video is on Unit 4, Polynomial Functions, Chapter 8, Intro to Polynomial Functions, Lesson number 3 on the remainder and factor theorems. This lesson is going to focus on using synthetic division and these two different theorems. The first one is called the Remainder Theorem. You're going to also hear me call it synthetic substitution. So either one of these refers to the same exact thing. Both of the theorems that we're going to look at today are going to involve synthetic division, which we did in lesson number 2. The thing is that the end result is going to be used to interpret differently so that we can answer different types of questions. So if it says divide, we would use just what we learned in lesson number 2. If it talks about evaluating, we're going to use this remainder theorem. And if it asks you about factors, we'll use the factor theorem. So let's look at this remainder theorem first. Let me read through these bullets. The remainder theorem is used to evaluate polynomials at a given value of x. Now, when we say evaluate, that just means to substitute. So there is a calculator way of doing this, but we are going to focus on using synthetic division to do it. You're going to let f of x be any polynomial of degree greater than or equal to 1, and let a be any real number. If f of x is divided by the polynomial x minus a, then the remainder is f of a. So basically what that means, all of that just means that when using synthetic division to evaluate a polynomial, the remainder is the answer. So for the remainder theorem, when we use synthetic substitution, the remainder is what we're going to focus on. What is my remainder? Because that's my answer. The directions in these examples tell us to use synthetic division or synthetic substitution to evaluate each polynomial for the given value. So just like we did with synthetic division, we want to make sure that it says x is equal to. So looking at example number 1, it says f of x is equal to x cubed minus 4x squared plus 3x minus 5. And we want to evaluate that if x is equal to 4. It already says x equals, so I don't have to change anything. I don't have to do anything to that. That 4 is what's going to go in our little box to the left. We're going to look at our polynomial and see if it's in standard. It is. It starts with an exponent of 3, then it goes with 2, then a 1, and then the constant. So it's already in standard. There's nothing that's missing. I'm going to pull down those coefficients just like we did in lesson number 2. Bring the first term down, put my little box where my remainder is going to go, and start multiplying and adding. 4 times 1 is 4. Negative 4 plus 4 plus 4 is 0. 4 times 0 is 0. 3 plus 0 is 3. 4 times 3 is 12. Negative 5 plus 12 is 7. So my remainder is 7. To write my answer, what this means, the remainder is my answer. The f function when x is equal to 4 is going to be 7. Now, what did this look like before synthetic division? Well, before synthetic division, we were substituting the 4 in. So we were probably using our calculator to evaluate this whole entire thing by substituting in the 4. But again, synthetic division can be used in its place. Let's jump down to number 4. Looking at example number 4, p of x is equal to negative 3x to the 4th plus 3x squared plus 9 when x is equal to 2. So again, we're evaluating this for x is equal to 2. Put the 2 in the box. The one thing I do notice as I'm checking for standard form is on number 4, I'm missing a couple of terms. So we have an x to the 4th, but we don't have an x to the 3rd. So I'm going to put a 0x to the 3rd here. And we have an x squared, but we don't have an x. So I've got to hold that spot, just like we did with synthetic division. When we are setting up for synthetic substitution, we have to make sure we hold everybody's spot. So there's the negative 3 for the x to the 4th, 0x cubed, 3x squared, 0x, and then my 9. And again, the remainder is what I'm looking for. Multiply, 2 times negative 3 is negative 6. 0 plus negative 6 is negative 6. 2 times negative 6 is negative 12. 3 plus negative 12 is negative 9. 2 times negative 9 is negative 18. 0 plus negative 18 is negative 18. 2 times negative 18 is negative 36. And 9 plus negative 36 is going to be negative 27. So the p function, where x is equal to 2, is negative 27. All of these are going to be the exact same on this page. If you want to do some practicing, I can tell you that on number 2, g of negative 3 is equal to 4. On number 3, h of 3 is equal to 43. Number 5, k of negative 6 is equal to 219. And on number 6, w, where x is equal to negative 2, you should get negative 5. So those are some of the answers if you want to practice some more of those. What I want to talk about now is the factor theorem. If I were to say something like 2 is a factor of 12. The reason why 2 is a factor of 12 is because 12 divided by 2 is equal to 6 with no remainder. It divides evenly. And that's the whole premise behind this factor theorem. The factor theorem is an extension of the remainder theorem or synthetic substitution. If x minus a is a factor of a polynomial f of x, then f of a is equal to 0. So the remainder is equal to 0 here. The remainder equals 0. If the remainder is equal to 0, then we know that we've got a factor. The factor theorem links factors, roots, and zeros of a polynomial. Some of this is going to be a little confusing, and I will clear this up when we go through the assignment. But a factor looks like this, and x minus 2 is what we call a factor. When we talk about evaluating f of 2 is equal to 0, that means that 2, which is the x, is a root or a 0 of that function, which means it's one of the solutions for x. If a number is divided by any of its factors, the remainder is 0. So let's look at example number 7. Directions are telling us to determine whether the linear binomial is a factor of the given polynomial. F of x is equal to negative 2x to the third plus 3x plus 4, and our binomial is x minus 1. So the question here is x minus 1 a factor of our function? Is x minus 1 a factor of the function? In order to say yes or no, we have to use our synthetic division, and the remainder would have to be 0. So just like with synthetic division, we have to make sure that it says x equals. So I'm going to set this up and it says x is equal to 1. Once you add 1 to both sides, x equals 1. So we'll put the 1 in the box out to the side. Looking at standard form, it looks like I'm missing a x squared, a 0x squared. Everything else looks good. So I got my negative 2, my 0x squared, my 3x, and my 4. Bring that first term down. Again, I'm focusing on the remainder. The remainder should be equal to 0 in order for this to be a factor. 1 times negative 2 is negative 2. 0 plus negative 2 is negative 2. 1 times negative 2 is negative 2. 3 plus negative 2 is 1. 1 times 1 is 1. 4 plus 1 is 5. So because I have a remainder, that means that the x minus 1 did not divide evenly. That means that x minus 1 is not a factor, which means that 1 is not a solution. We're going to jump down to number 9. G of x is equal to 2x to the fourth plus 8x cubed plus 2x plus 8. And our question is x plus 4 a factor? So take the x plus 4, set it equal to 0, and we get x equals negative 4. So we're going to use the -4. And do we have all of our terms? It looks like we're missing the x squared again. So the 2 for the x to the 4th, 8x cubed, 0x squared, 2x, and 8. -4 times 2 is -8. 8 plus -8 is 0. -4 times 0 is 0, plus 0 is 0, times 0 is 0, plus 2 is 2. -4 times 2 is -8. 8 plus -8 is 0. So the remainder is 0 here, meaning the x plus 4 divided evenly. So what that means is that x plus 4 is a factor. What that also means is that -4 is a solution to the polynomial. But we'll talk more about that later. If you want extra practice, number 8 is a no. Number 10 is a no. 11 is a yes. And 12 is a no. But that wraps up the examples for lesson number 3 on the remainder and factor theorems.